Okay, welcome to Kerala MOOC's course page on uh, digital signal processing. Our discussion is on uh, discrete time systems. And now today we are going to discuss about Z transform. Normally these transform techniques are very important tools in the analysis of signals and systems. And especially in this case, we are all discussing about the linear time invariant systems. So here we will introduce a new transformation techniques, and that's what we call it as the Z transform. And in this lecture, we will develop, we will try to demonstrate its importance in the analysis and characterization of various types of linear time invariant systems. And we will see some properties of these Z transformations. So normally this Z transforms plays one of the major role in discrete time signal analysis, just like the role which is played by the Laplace transforms in the continuous time signals systems. So here first of all we will see the Z domain, and you know about the Z domain. Z domain is something which is a complex Z plane, and why we use this type of transformation techniques is that because in the last chapter we studied the convolution of two signals, convolution of two time domain signals, and how to do the convolution sum, and we'll use a technique known as shifting, then multiply, then add. First of all we will fold the sequence. One of the sequence is folded, then we'll shift the other sequence, shift the sequence, then we'll multiply with the other sequence, then we'll add together. So it's a very complex process. Then if you use this type of transformation techniques, then the convolution becomes very easy. The convolution of a two time domain signals is equivalent to the multiplication of its Z transformation. That's why we use this type of transformation techniques. So that will greatly simplifies the analysis of the response of linear time invariant systems to various signals. And now let us move on to, and moreover this technique is very important in analyzing the stability of the system, whether the system is stable or not. We can analyze the system's stability by using the location of the poles and zeros in the Z. That we'll discuss later. Okay, now we will begin with the definition of a Z transform. So here we are going to define the Z transform. So Z transform of a discrete time signal x of n is defined as a power series. It's a power series of x of n, and the Z transform is x of a z is equal to the summation of n is equal to minus infinity to plus infinity x of n into z raised to minus n, where this z is a complex variable. And this relationship, this equation is sometimes we call this equation as the direct Z transform, because it transforms the time domain signal x of n into its complex plane representation as x of a z. So the inverse procedure is also is there, and we'll call it as a inverse Z transform, and that means we'll obtain x of n from this x of n can be calculated from x of z. If you know the x of z, then you can easily calculate the x of n. That means we can calculate the time domain signal from the z transform, z domains, the signals in z domain. If you take the inverse transform, inverse z transform of this x of z, then we'll get the time domain. That's why we use this type of transformation is. Now, so normally we will represent x of z as, for convenience, we will use z transform of a signal. X of n is denoted by x of z, and normally we use a capital Z, and or sometimes we'll use a symbol like z of x of n. And sometimes if you want to represent in relationship, then the relationship between x of n and x of z is indicated by x of n and x of z. So in the z transform, so here that's one of the method that we normally used.